the molecular can travel between collisions, before collisions. Before collisions, how far does a molecular can travel? So we consider volume of V, okay? And in this case, we consider like a nitrogen, okay? A nitrogen. So, you know, because of the thermodynamics rule, these nitrogen gas molecules is filled of high energy. So we have a velocity. We have the velocity because of the thermodynamics rule that they only have no velocity at 0K, which means any molecules above 0K have the kinetic energy. And this is a velocity, and this is the mass of the nitrogen atoms. So altogether, we can calculate the kinetic energy. And this is how many numbers of the nitrogen molecule in a specific volume, okay, in a specific volume. And the mean free path is something that the molecule is moving, and this is how each, for the next time you see that is how far it goes. This is, we call the mean free path, lambda. And there is another term, which is diameter, D. This is a diameter of the molecules. All right, so we have the length of how far it travels. Okay, this is a mean free path, and diameter of the gas molecule. So the impact parameter is how we can calculate is pi d squared, right? This is pi d squared. This is the pi d squared times the lambda, and the volume swept out by one molecule between collision is the lambda pi d squared. Okay. So so this is we just bear in our mind that the volume between collision is lambda pi d squared. Lambda pi d squared. Lambda is a mean free path. This is a cross section. So the total volume of sample is times n times lambda pi d squared. So the lambda equal to V over number pi d squared. And when V over n, it can be more accurately can do this calculation. Lambda equal to square root 2 divided by 2n pi d squared. If that is using the ideal gas, the n equal to n divided by volume, which is P over kBT. So this is a number of molecular divided by the volume, and so we can have a lambda and replace the n divided by V to P kBT. Okay, so we can make the lambda equal to 2 pi d square root 2 P over kBT. So the lambda mean free path is proportional to the temperature. So if you have a higher temperature, then you have a higher mean free path. The other way if you have less pressure, if you are in a vacuum, then you will have higher mean free path. So this is one ATM. The mean free path is 10 to the minus 5. When you reduce one ATM to one torr, okay, one ATM equal to 760 torr. Okay, so if you reduce to one torr, the mean free path will increase, okay, to 3 times, 3 order. So from 10 to the minus 5 centimeter to 10 to the minus 2 centimeter. Okay, so one torr. And 1 torr, this is where most of the vacuum technology, the operating pressure, okay, operating pressure of the vacuum technology. And in the 1 torr, you have a 10 centimeter length long. So this length is 10 centimeter. So imagine the 10 centimeter is something that you stretch your fingers, okay? And this is about 10 centimeter in the one mini torr, where the plasma generated, okay? So in the plasma generated pressure, 1 torr, you have a mean free path of 10 centimeter in its length. So what is a flux of atoms heating surface unit time? This is a flux which is equal to number of the molecules divided by the area and divided by the time. Okay, so this is an area and this is time. Then the J flux is nVx. This is the velocity, okay, velocity, and divide by 2. Okay, so calculating the gas velocity, well, we know that the gas is something like a Maxwell distribution. Okay, it's just like a distribution. Okay, the Maxwell contribution. So, and this part is a kinetic energy, okay, mv squared divided by 2. And the K is a Boltzmann constant, T is a temperature. Okay. So when you try to integrate the Maxwell speed, okay, and with its velocity, you will integrate that and you generate kinetic energy equal to 3 divided by 2 kBT. I think we in the college we have understand this is calculated by the Newton's law, right? This is Newton's law, and so the Newton's law, the kinetic energy can be proportional to the temperature. And this temperature is absolute temperature in the unit of Kelvin, And in the other way, you can say in the x direction, which is 2kT over pi m, okay, over pi m. And for the v, which is 8, all right, 8 kT divided by pi m. And for the v root mean square, okay, which is 3 kT divided by m, 3 kT divided by m, that is your velocity. And the root mean square is how you get your a significant velocity of the gas. Okay, so this is a so-called gas kinetics. So we understand the velocity and the velocity and the relation of the velocity and the flux in the x direction, okay, which is n divided by 2 square root 2 kt divided by pi m. And then if we assume the ideal gas, PV equal to nRT, so you can generate the J flux in the term of pressure and temperature. Okay, so compare this flux to the mean free path. Okay, so we can using the this force divided by area equal to E kinetic energy divided by the volume VOL, and you got the flux times momentum. Okay, so pressure is molecular momentum. Pressure is molecular momentum times flux. This is molecular momentum, and this is the flux. And that is the pressure. Okay, and the pressure is a force divided by area, right? The for a specific surface area and how much intensity of force. So, and that pressure can be expressed as the molecular momentum times flux. Okay. So if you make it put it the number, and you will see the Jx is in the following expression. So if the gas is at 10 to the minus 6 torr, okay, the flux is 1 mole layer, okay, 1 mole layer per second. Okay, so this is quite important. That's the reason in the remember in the semiconductor characterization, we normally operate the pressure, the vacuum pressure, under the 10 to the minus 6 to confirm the monolayer arriving per second. Also, there is a diffusivity. The diffusivity in the solid, this is because of the chemical potential. This go here, and this is another we call the Debye expression, which is diffusion equal to diffusion coefficient times exponential minus delta G divided by KT. So for gas, no energy barrier, only collision, we have the D gas, which is about lambda times V in the one direction divided by 2. Okay, but we already talked about the mean free path as a function of temperature and the pressure, right? We talk about that. So if you make this plug into here, the D gas will be proportional to the temperature in the power of 3/2. And it will be inverse proportional to the pressure. Okay. So I think this is quite important relationship we need to understand. All right, so again, mean free path. The relation of the mean free path proportional to temperature inverse proportional to pressure. And 10 centimeter at pressure 1 millitorr. And 100 meter at 10 to the minus 6 torr. And 10 to the minus 6 torr is equivalent to 1 mole layer. Okay, and this is 100 meter, which is the mean free path of the gas. Okay, and we understand this is a Newton law. This is kinetic energy, and this is proportional to the temperature. And so we can do the calculation of the flux. And this flux is in the relation of proportional to the pressure. More pressure, more flux. More temperature, less flux. So we have a weak temperature dependence relative to solid state diffusion. Okay. So when we talk about the vacuum, there is a number called the Knudsen number. This is a dimensionless number, okay? And this is very useful to make sure the condition of a gas molecules in a reactor. So let's say the capital L is a dimension of a chamber or reactor, okay, L. And just draw your attention again that the mean free path is proportional T, inverse proportional P. So, and we also want you to memorize this, right? 1 millitorr, 10 centimeter, 1 torr, 10 to the minus 5. We already say that. So the Knudsen number is lambda, which is mean free path, divided by L. L is the length of the chamber. So if lambda divided by L less than 1, which means the mean free path is far less than the reactor. So in this case, the flow is viscous. And this is something where pressure, the vacuum pressure, is larger than 1 millitorr. So the pressure larger than 1 millitorr, the gas flow is viscous. Okay, you need to memorize this line. You need to memorize this line. This is very, very important. So when the pump power must be larger than the viscosity and must transport large number of molecules. When the lambda divided by L less than 1. In the other situation where lambda divided by L greater than 1, in this case, we have mean free path far larger than the reactor. And this is a molecular flow, or you say it's a ballistic flow. Okay, and this is a pressure, the vacuum pressure, less than 1 millitorr. And at this case, pump efficiency become critical. Okay, become critical. And so in this case, if you want to reduce the pressure, you must attract in the whole molecules. Okay. So this is the case that we talk about the pumping speed. Okay, we talk about the pumping speed. The pumping speed, we can say that the conductance of vacuum component, this is the side from 1.1 to 0.2, and this is a pressure difference in the time is equal to the velocity times the gradient pressure, which is the difference of the pressure times velocity will be the change of the pressure versus time. It's a kinetic. Okay. So this is a conductance of vacuum component, and this part is a pump throughput, which is how fast you can remove the molecules. Okay, how fast you can remove. And so this Q express flow as a number of molecules over time, dt dn. And dt dn, it can be kBt, v dt dp, and p dv dt, because n is equivalent to pv over t, right? PV equal to nRT. So n equal to PV. So divide by t. And you do a total derivative on the PV, which become V dP and P dV. Okay. And this part, pressure times volume change with time, is the pump throughput, and the volume times pressure difference. Okay, pressure difference will be the conductance of vacuum component. Okay, so the pumping speed will be S equal to V divided by kBt times T. So normally pumping speed, we use a unit of SCCM, okay, or liter per second, okay. And SCCM is standard cc, which is volume, divided by minute, or liter per second, okay. So I was saying that the vacuum technology generating a low pressure and two classes of vacuum pump. Okay, the first type is molecular physically removed from chamber, such as the mechanical pump, turbomolecular pump, oil diffusion pump. These are all molecules physically removed from chamber. There is another type, which is molecules adsorbed on a surface, all right? Something like ion pump, okay, or cryon pump, which is adsorbed molecule on a specific surface. Okay, so please memorize this. Okay, memorize this. So molecules physically removed from the chamber. We have mechanical pump, oil diffusion pump, and turbomolecular pump. And this is quite a good pictures. It gives you a range, the range of the vacuum it can reach, okay? It's from 1 atm to 10 to the minus 9 torr, okay? 1 atm down to 1 milli torr, which is 10 centimeter mean free path, right? And going further, 10 to the minus 6 torr, which give you 100 meter. Okay. So this is a range. The oil diffusion pump probably goes to 10 to the minus 6. If you want to go further, the turbo molecular pump is a better candidate. Okay, so please remember this slide. The other type of pump, vacuum pump, is where molecules adsorb on a surface. Okay, and like a ion pump with titanium sublimation or cryon pump. Okay, and the cryon pump is somewhere can operate in 10 from 10 to the minus 6 torr to 10 to the minus 9 torr. And the ion pump also can do a pretty good job in this way. Okay, so this is quite a good table that help you to understand the vacuum pump. Okay, so let me do a summary on the pump. We have two classes of vacuum pump. And we have a molecular physically removed from chamber, which is mechanical pump, pump from 1 atm, and turbo molecular pump, pumping from 1 millitorr, and oil diffusion pump, and no moving part because it just really trap the using the oil diffusion and the oil in vacuum, and we use that as a driving force to remove the gas molecules. And this second type of the vacuum pump is molecular adsorb on a surface, like ion pump is clean, okay, quite clean. The pump reactants, no moving part, and pump from 10 to the minus 4 torr. And the cryon pump is the same, clean, no moving part. Okay, so most systems use different pump for different pressure range. I think you should understand that there must have at least two pumps, okay, at least two pumps for a high pressure system. For example, if you want to reach to 10 to the minus 6, you have to use mechanical pump first, because pump from 1 atm and pump down to the 1 millitorr, and then using turbomolecular pump because the operating pressure is starting from 1 millitorr and then go down to the 10 to the minus 6 torr, right? Or it goes down to 1 millitorr, and you can use ion pump to keep reducing the vacuum. So we normally say the standard vacuum is 10 to the minus 5 to minus 6, which is a standard. Okay, and like a CVD, thermal evaporator, sputter, we use 10 to the minus 5 to 10 to the minus 6 torr. And there is another vacuum called the ultra high vacuum, which is 10 to the minus 6, 8 to 10 to the minus 11 torr. And, you know, this is a case we are doing the material characterization, okay, characterization. So normally, if you want to go down to the ultra high vacuum, okay, then mostly, in the most case, you need to bake in a stainless steel ultra high vacuum system with a 200 degrees C for hours. Okay, and in that case, you will find that the water vapor desorption, sometimes organics from chamber wall, can be removed. So, so baking is a tool to reduce the ultra high vacuum system. Okay. So let's talk about the thin film growth. Okay, let's talk about that. The thin film growth generally, you see, in this case, this is a film is an island, and then coalesces. Okay, and this bounce with three sides, one side, second side, and the bottom side, three sides. And here only bounce on one side. Okay, so it's only one side, and then it tends to have more bounce. Okay, so we always consider about the arrival, sticking, and surface diffusion and the bonding. So the film, the rate of arrival, this is a rate of arrival, divided by the diffusion rate, it will be the R. Okay, and this diffusion rate is something like arrival and diffusion and growth. Okay, so the first one, you see that film growth competes with gas arrival. This is gas arrival, and this is film growth. And we are trying to comparing which part go faster, the film growth or gas arrival. So in the case R greater than 1, so non-equilibrium and the fast growth may misaligned island and leading to defective. So which is gas arrival larger than diffusion rate. You always leading to a defect sites. Okay, defect sites. So like a polycrystalline film, like a column grains, okay, and this mode we call the Weber mode, all right. And in this case, normally generate amorphous film. Okay, the second case, the R less than 1, which is diffusion rate larger than the arrival rate. In this case, you have a slower, more equilibrium layer by layer growth. And in that case, you will generate a larger grain. Okay, you will have a larger grain and raise surface temperature. And your mobility in the case, if you increase the temperature, you have a higher mobility. Okay, so this is how we can generate larger grains. If film and substrate have the same crystal structure, and then we say this is epitaxy, okay? And this is a two-dimensional growth. And this is, we call the Frank van der Meer mode, okay? So please memorize this one. This is a mechanism of thin film growth. Okay, the mechanism, and R greater than 1 is Vollmer-Weber mode. R less than 1, we have a Frank-Vandermeer mode. Okay, please try to memorize this. This is quite important. Okay, and I think this is quite a good picture for you to understand. And this is also quite a good picture telling you this is faster or this is faster. So for the thin film growth less than 1, okay, less than 1, you have a higher diffusion rate. So if you have a higher diffusion rate, let's see the mechanism. The arrival rate, and then physical adsorption, and then surface diffusion. You get a chemical reaction, nucleation, and growth, and then bulk diffusion. So in this case, you got a better quality film, and you will see a layer by layer growth. Okay, but if R greater than 1, then you found that the process 2 to process 6 have reduced probability. You have less probability to generate from 2 to 6. And as a result, you have a poor quality and rough film. Okay, so I think this is quite a good model that help you to understand the condition to generate better quality films. Okay, better quality films. You have to make sure the thin film growth are less than 1. And how do you control and make sure the diffusion rate always larger than the rate of arrival? So the way that we know how to control is back to the Knudsen flow. And you remember I have mentioned about the Knudsen number, which is a mean free path divided by the length of the reactor. And if this number less than 1, Knudsen number less than 1, the flow is viscous. If Knudsen number larger than 1, this is a molecular flow. Okay. And in this case, the deposited species arrive in a hot way, and the growth ballistic, and you've got the shadow effect, and the step coverage is not going to be good. However, if the flow is viscous, you will see the deposited species which is thermalized, and the growth is from all direction, and a good step coverage. Okay, so so what does the Knudsen number tell us about the film growth? So we are talking about the thin film made by a variety of films, the PVD. And the PVD, it can be thermal vapor deposition. We call the evaporation. Or we can use sputter, which is DC magnetron, or RF for oxides. Okay, and DC is the magnetron for metals. Of course, we talk about the CVD, chemical vapor deposition. Okay, so this is the whole film growth. Okay, so I'm going to stop here, and um, we will take a 10 minutes break, and then I'm going to go to the next slide, which is um, which is physical vapor deposition. Okay, and so before I the before that, Iran, can you help me to do the check-in? If anyone help me to check the if all the students has come.
好，然后所以叫他们就是视讯吗？
可以，然后就开一下那个声音不用开，然后把那个大头照，就是那个实际的秀一下，然后办法全部人都看得到人头吗？
我可能要试试看。
好，你试试看。好，那我们就到7点，你就 check，然后我们7点半再上下一节课啊。
好
好，那请你来帮忙确认一下，或是你就是你有问题再告诉我好吗？
，OK，来，哎，然后老师，然后我可能这边要先请你结束你那边的分享荧幕。
好，我看一下怎么做，等我。
就是
哦，
它有个，
好，我看到了，我看到了，
然后
对，关了哈。
好，然后我再看一下哦。哦，有了，好，各位有开相机吗？好，我这边有一个人呢，2个人，我这边4个5个，印组，Hello，7，哎，看一下相机吧。
哎，
然后，
那你都在你的荧幕上，对不对？
对，我待会用那个画面截取，
好好，
刷一个，还有一些人你那边看得到我
还有谁？你要不要叫一下？嗯，
上帅哥那个我不会念，不好意思。然后凯哲、子宁、班长、一心、一群啊，有了，一心、子宁、一群哦，你有了，我都还没看到，因为你开了2个嘛，你应该电脑跟手机各开一个，抱歉。哦，有了，诶，那一群有吗？一心呢？哦，有看到了一心。哦，子宁一群你是黑画面哦，还是你比较开玩笑的，不要乱开。仲凯，没事啊，没事。仲凯有，先不要关好了。哎，仲凯你又关掉了。还有这个凯哲吗？王凯哲，看剩他我就按下去了。
好了，你先按吧，你先按吧，别人等一下又有人 See you at 7:30.
我知道我大概开了双荧幕超啊，我忘记关。
Okay, so we're back to the So we're back to the physical vapor deposition, and I hope this make you better. We talk about the CVD, and it is the gas phase reactants in the 1 minitor and purging into the reactor. And we always find a good step coverage, right? And we also have a plasma enhanced CVD, and the plasma enhanced surface diffusion without need for the elevation of temperature. Okay, so you don't need a very high temperature, and that part is contributed by the plasma. So we will see the evaporation, which is the evaporating source material. Sometimes we make the pressure less than 10 to the minus 6. And of course, in this condition, in this low, very high vacuum or very low pressure, the step coverage is poor. Okay, and so we will also talk about the dry aging by using the plasma. Okay, the momentum transfer and the chemical reaction from plasma to remove surface species. So we call that as a dry aging. So now we are going to talk about the sputter deposition. Okay, and normally we are using 10 to the 100 millitorr, right? And so what is a plasma? We have talked about that. Okay, we have talked about the plasma and okay, so a gas plasma is a gas of ionized particle, and typically of noble gas, and this is argon. We prefer using argon, and with its electrons. So we have talked about the plasma, and we talk about that it's ionization process. And so we are using the cathode and anode, and there is a voltage drop, and that voltage drop make the separation of argon ion and electron. The electron go to the anode, and the argon ion go to the cathode, right? So do remember, we are using the sputter. Later on, I'm going to talk about the sputter, and the sputter is utilizing this part. 等一下我会讲到键度啊，键度就是利用这个部分，用阿港去撞击 cathode. Okay, so the ionization potential of argon is about 16 electron volts. Okay, 16 electron volts, and the plasma occur at 10 to 100 millitorr. Okay, 10 or to the 100 millitorr. So plasma is self-sustaining over a range of pressure. Typically, it's a 1 or 10 millitorr, right? And it should make sure it is located in this range. Okay, if the pressure larger than 1 millitorr or even larger than 1 millitorr, you will see that the plasma is difficult to generate. Okay, it's difficult. So to understand why this pressure range, we need to understand what goes inside the plasma, what's going on in the plasma. And if we understand the mechanism of the mechanisms on the plasma, then we understand why we need a pressure range in this one. So this is quite a good information. And let's see what is molecular density at 10 millitole. 10 millitole, this is 10 millitole. And this is one torr, okay? And this is 1 atm. If this is a 1 atm, the density, okay, is 2.5 times 10 to the 25. All right, but if you reduce the pressure to here, the density becomes 3.2 times 10 to the power of 20, 10 to the power of 20, okay? And the mean free pass of 10 millitorr is around 3 centimeter, okay? Around 3 centimeter. So at 10 millitorr, the molecular spacing is around 0.15 microns, right? So this is a N, this is N, and it in a cubic, right? In a cubic. So if you make it in the one direction, one dimension, make it one dimension, it becomes 0.15 micron. Okay, but this molecular spacing, is this molecular spacing equal to the mean free pass? If you remember, we already talked about the mean free pass of the mean free pass of the 10 millitorr, right? So spacing between molecular is 0.15. The mean free pass is 3 centimeter. This is 3 centimeter mean free pass. And this is molecular spacing, which is 0.15. So we can also do the calculation of thermal velocity. Thermal velocity is square root of 3 kBT divided by m, right? So you will see it is almost 10,000 meter per second. So the velocity is quite high. Second per, you can say this is 1 kilometer. 1 kilometer per second. So it's very fast for the thermal velocity of argon. So the final velocity of ions at x equal to lambda, we can do a calculation. And this calculation is V final square equal to V0 square plus 2ax. This is Newton's law. Okay, Newton's law. The acceleration times the length, the distance of the acceleration. So we have this one, all right, and this can be proportional to the e times Q divided by M times lambda. So what we are talking about is the argon has a velocity of 4 times 10 to the power of 5. The electrons has the power even 2 order larger, 10 to the order of 7. Why? 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 Why it has 2 order? 2 order difference.
Professor, electron is smaller than atom.
Right. So if we share the same momentum, the velocity will be is inversely proportional to the mass of the argon ion and the electron, right? So this is a reason the electron has a faster velocity. Okay, but in this case, the problem is only 0.1% to 1% of argon are ions. Okay, so this is the difficult part. The difficult part is the density of argon ion is very low. So I have talked to you that we can make a high density plasma, okay, later on. So, so we have different velocities. We have V kT, which is 10 to the 3. We have V argon, which is 4 times 10 to the 5. We have V electron, 10 to the 7. All right. So we have different velocity. And since we have a lower velocity of argon and high velocity of electron, and so it will just ionize, and the plasma is highly conducting due to the electrons. So we have a flux equal to N times charge times Vx. And we found that the flux of electron is far greater than the argon, at least in the 2 order, right? In the 2 order. Okay, so so plasma is self-sustaining in the range of 10 millitorr to the 100 millitorr. Okay. So necessary condition, if pressure is too low, the mean free path is very large. So you have less collision in plasma. And if you have less collision in plasma, you don't have enough energy to make sure you sustain the energy. Okay, so lambda less than if the lambda less than the L is a reactor chamber length, you found that collision exchange energy with plasma is the following. We have talked about that. But if pressure is too high, in that case, lambda is small. The pressure high, lambda small, and very little oscillation between collision, because you don't have enough distance to isolate your ions before it collides, right? Makes sense, right? That's the reason. If you want to generate plasma, the pressure cannot be too high, cannot. All right, and also the necessary condition for the plasma is a kinetic energy has to be larger than the ionization potential. So we found that this is a region of self-sustained plasma. Okay, self-sustained plasma. And this is a slope, okay, for the 100 volts. This is 1000, and this is, I think this is, let me see, it's about 0.15, the mean free path, less, in this case, lambda less than L, and it's almost, the lambda is almost 10 centimeter. Okay, lambda is 10 centimeter. Okay, and 10 to the, and also we know that the mean free path, okay, of the gas molecule in the 10 millitole is 3 centimeter, right? This is what we have talked. Okay, in this pressure, the mean free path is 3. So this is 3. This is also 3. So let's talk about the glow. Okay, the glow is what happening is when argon impact on cathode, and you found that a lot of electron come out, right? So this is where it hits, and there is a lot of electron come out, and this is the in the 1 point electron volts, you start giving a glow and keep increasing the kinetic energy. You have from glow to the ionization, and this is the whole region is the is a glow, right? And this is a cathode, this is an anode, and we say this is a black sheath. Okay, and in here we also say this can be a we call the Faraday dark space or dark sheath. Okay, so cathode dark sheath over here, and anode dark sheath. So you see the cathode dark sheath and anode dark sheath. Okay, and the electron induce optical excitation of argon. So you can see a glow, which is visible, 发红, 发红. So inside plasma, what is going on inside the plasma? Inside the plasma, you will see that this is a cathode, this is a cathode, and this is an anode. This is anode, and we are using the argon collides on the cathode and collides on. You put the target here, and then the target species come out to the substrate. So this is the theory of sputter. Okay, this is a theory of sputter. The argon ion hit on the target, and the target species come out. So, which species electron or argon ion is more likely to dislodge an item at electrode? So this is a cathode, and the cathode we say is a target for the source material. And this is an anode, and normally we use 1 kilo voltage. Okay, and the argon ion hit on the target, and then the target come out. Sputter remove occurs here. Okay, and you see there is a momentum transfer, and the electron is m times v. Argon is m times v as well. So which is 43 times of the momentum of electron. So 43 times. That's the reason we prefer to use argon, because argon is more efficient because it has 43 higher momentum of electron. So so we understand that from ion implantation, we understand most energy transfer, okay, when it hit on the target. So incoming particle has mass close to that of target, which is the best. You can come out with the best result. So the sputtering process is the argon impact or momentum transfer at cathode and release the target atom. So like a billiard balls, this is a billiard balls, and this is a red ball. When it hit, all come out, right? All come out. And how to do the calculation? We can use the elastic energy transfer. Elastic, which doesn't lose the energy, means elastic. 弹性碰撞. So that this is the result coming based on the momentum and the energy transfer. Okay, so you have two different mass. Okay, you have two different mass, and this is how it come out. So for the electron hitting on the anode, substrate is far less than. So you have the result, which is because M1 is far less than. So you don't have M1, you have M2. Okay, you have M2, and then you left the M1 here. So E2 over E1, you got a M2, all right, and M1 is 2 M1. Okay, so but electron can give us electronic kinetic energy because it will occur as a inelastic collision. So you lose the energy by collision. Okay, okay. So excitation of atom or ion only. So the sputtering process in the easy word is ablation of target. Ablation, what is ablation? 你们如果去查字典 ，ablation 应该是叫类似脱离脱离剥离剥除剥离，那就跟我们讲的剑度是一样的。Okay, so ablation is something like to remove from, and we now understand the argon has efficient momentum and energy. So we use argon to hit on the cathode, and when it hit on the cathode, we put the target in front of the cathode so that the target material is removed or is aging or is ablated in the verb, and ablation is in the noun. 一个是动词，一个是名词啊。So mostly we understand that in the case, in the ions, in the plasma, we say it's neutral because we have the same number of electron and the same number of ion. Okay, and the momentum transfer of argon on cathode erodes cathode atom. All right, and then it generates a flux to anode, to the substrate. So erodes, E-R-O-D-E, is similar to corrodes. Corrodes is chemically erosion. Erode is electronically corrosion. So target material normally, hopefully, must be conductive, right? Must be conductive. So in that way, it has to be metal, okay? Otherwise, you have to use radio frequency sputtering. Makes sense, right? So if you are sputtering a metal, you can use DC, you can use the you can use any power, RF, MF, as long because it is conductive. However, if the target material is an oxide, the oxide is not conducting, then in that case, the cathode cannot be used as a DC. 你的这个靶材，我们叫靶材，一定是要导电。导电的话，你可以用各种可能的能源 ，DC、RF、MF 都可以。可是如果你是氧化物，不导电，你就没有办法用什么？没有办法用 DC。Okay, so this is a part, and how it happened the deposition. Argon acylate to cathode, acylate to cathode, argon, cathode, in hit on the surface, okay, and the aluminum as a target erode or ejected and come out to the outside anode. Okay, so the first step, argon acylate to cathode. The second is you have a neutral target species pickoff. This is a target species and it's neutral, okay? And then some argon you ionized to argon ion, okay? Argon ion. You also find the argon ions combine with electron and become argon again. And argon excitation and make as a argon ion and electron. Okay, so repeating. Electron may ionize impurity, something like make the oxygen to the oxygen ion, but that has to be high energy. And you find a flux, we say it's a deposition. Okay. In addition to the aluminum atom, you also see some argon and some impurity as well. Okay. And then step 6, some physical resputtering of film by argon. It come up because hitting the argon hit on the aluminum and aluminum come out. Okay, so you need to memorize this picture. You need to memorize this picture. So the sputtering rate of material in target is a parameter, very important parameter. Normally, we have 0.1 to 3 target atom release per argon incident. Okay, but that is just a general. Okay, but it's quite a good thumb of rule. That's quite a good experience. 这是一个很好的经验啊，就是你有多少个氩撞击，大概可以撞出，只要有一个氩，就可以撞出0.1到3个靶材的原子啊，这是一个，就是说一个经验式啦，经验值。However, the sputtering rates are very little from material to material. Okay, sputtering rates, because I will explain that. Because vapor pressure of source not important. So this differ greatly for different material. So you got a neutral target species kickoff come out, right? And come out, this is aluminum come out, hit on the anode, and it become aluminum film. However, there is also argon will hit on the anode, which make the aluminum come out. So this is some physical resputtering of aluminum. This is not we want. This is not we want, because it will reduce the deposition rate. It reduce the deposition rate. So that's the reason we say sputtering rate vary little from material to material. We'll explain that. So we defined a sputtering yield. You need to memorize this definition. Sputtering yield. This is the number of incident ion in the denominator, the number of atoms molecular from target. And this sputter is proportional to the cross-section area, ID squared. Okay, and proportional to the area, number of area. Okay, and proportional to the energy. This is energy ratio. The top one is excited in each layer, and in the denominator is threshold, the energy to displace interior atom. We call that threshold energy. So, and then comes out the square root of E2 divided by EB. And EB is surface binding energy. Okay, so binding energy, you got a larger binding energy, you have a less sputtering rate. It's quite easy to remember, right? Larger binding rate, less sputtering yield. Larger threshold energy, less sputtering yield. Okay, I hope you can memorize this. Okay, so what is E1 and what is E2? Okay, and what is EB? EB, the surface binding energy, the surface atom removed to the vacuum stage. This is EB. All right, EB, and so this is incident energy, and it come out to the interior. All right, so we say the threshold energy is energy to displace this interior atom. Okay, energy to display interior atom. So so we got this quite a good equation to express the sputtering rate. The sputtering rate depends on angle of incidence as well, and masses and the kinetic energy. So you know, it's the sputtering rate, and this is the angle of incidence. So you see that in near 90 degree, you have the almost the highest sputtering rate. Okay, so this is 0 and become higher. Okay, so I think this is quite a good information for you. You can try to check this book, okay? And there is a table, and due to the copyright, so the author take off this, and also this one figure you can check. So finally, let's talk about the sputtering. We talk about the isotropic flux and anisotropic flux. This is isotropic, right? All direction the same. This is anisotropic, okay? So more narrowly directed at surface. And the surface roughness come out, poor stack coverage. And in the higher P pressure, you got the normal component, okay? You finally got a good step coverage. And so this is the way that we do the estimation on the sputter step coverage. So if you have a moving substrate, sometimes you got a moving substrate, or sometimes you got a situation that you have a very large target and a very small substrate. Okay, all come out to this result, more uniform thickness. All right, but if you got the high pressure, you got a shorter mean free path. High pressure, you got a better stack coverage, but more trapped gas. So this is, we talk about 10 mini-torr, you got a mean free path. In fact, in somewhere in the previous slide, we said it's 3, right? So, you know, just between 2 and 3. So the target composition versus the film composition. Well, we understand sputtering is to remove the outer layer of target. So normally we lead to a problem. We found that the problem with multi-component system, all right, at the beginning, because there is on the surface, there are something impurity on the surface. So initial target composition, A, B, if we have surface composition of target, you got A3B, A2.5B, and A2B. So you found that the surface composition of target A keep decreasing. If the sputter U, A larger than B, you got the problem, and it changed with time. So that is a very phenomenon bother us very much. So deposition of the film, you will find it is rich in A initially. Okay, so there is another approach, which is I co-spatter, 共建度, co-spatter. So you spot, you have a target here, A, and target B, and we co-sputtering, and then you found that there's A, B, A, B, A, B, 2. So, sorry, this is A to B, AB, AB2. So this is a challenge. I think this is quite a challenge to us for the co-sputtering. You want to sputtering AB at the same time. And this is another case that, for example, this is an alloy. 这是一个合金 A3B 的合金 and you find that it changed with time. Okay. So some other sputtering experience. If you're using the DC sputter and you found that DC sputter only work for the conducting material. So if DC were used for insulator like a carbon, charge would accumulate an electrode, each electrode, and the quench plasma. Okay, quench. So quench is something that 熄火. So your plasma become disappear. Okay, so of course 1 microsecond quench plasma with 1 to 10 microsecond. It just the lifetime is very small. Okay, the lifetime is very small. And as a result, if you are using a non-metal, you need to use a radio frequency plasma. Okay, so RF sputter system is basically a capacitor with gas dielectric. So RF plasma sputtering, the target is here, generate the plasma. So the plasma conducts at the low F. Okay. And V equal to 0 in the plasma. So plasma potential still, you see the V, plasma V is larger than 0 due to the high velocity of electron and charging on the surface. So the mobility of target species still sputtering in half circle. And so you see that it goes down like this. From here, it goes down by the argon hitting on the target. So we talk about that, the smaller target, you found that the field become higher. Okay, the area, the smaller target here, and higher field. Because this is inversely proportional. So we have a frequency, radio frequency, 13.56 megahertz. That's quite just a frequency, 3.56 megahertz for sputtering, RF sputtering. Okay. The other thing we need to consider is a bias. the bias is the potential we provide. Like in this case, we always give voltage as 1 kilovolt. However, we can generate a bias for like -100. So this negative and this is negative. So negative wafer bias can enhance resputtering of film. That's quite interesting, right? You attracts it back. So resputtering of film. So bias is more handled for process control, right? Like we talk about the silicon, it's denser, and then if you using the bias, it induce its stress, the resistivity, density, dielectric constant of silicon. So that's quite interesting that the bias can affect the film quality, including the stress, including the dense, including the electrical resistivity. So it's quite an interesting topic that we would normally use bias voltage to, especially negative wafer bias, to enhance resputtering of film. So film stress in RF sputtering is following. We have a bias, make a bias negative. So it will attracts the ions, okay, attracts the ions. And then you see the panning, thrilling, microvoid collapse, and even a bigger, it generate microvoids. That's quite a something that we don't want it to happen. Microvoids, which are in the other ways cracks. 微洞，微缺洞啊，我们或是叫做这个 cracks， 就是微裂啊，微裂。So in this part, we increase the pressure. Increase the pressure. Pressure, you got a larger grain, and in the other side, we increase the kinetic energy. Okay. So finally, magnetron sputtering is what widely used, and this is a cathode. On the back of cathode, we put magnetics, NS, 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 and we know the magnetic lines, string lines, go from N to south, N to south. So we have this magnetic string lines, okay? And then we understand this is a Lorentz force, I already told you. And it's a V cross B plus electric field times charge, okay? So it generates a spiral, 螺旋, around B field lines, okay? So this is a spiral line it generates. And what is the advantage? Because B field enhance time of electron in plasma. And then we have more ionization and greater argon density. Okay. And the other type, we talk about that. sputtering target has to be conducting, but you don't want to make a conducting. You want to make a oxide or nitride. In this case, we use titanium. Okay, titanium as a target, and we provide, in addition to argon, we apply nitrogen. So in the nitrogen, we generate the titanium nitride. Okay, so similarly, you can use silicon nitride or ferrite nitride, and with oxygen, you can do the silicon oxide, titanium oxide, chromium oxide. So remember I talked about the thin film growth detail when rate of arrival less than diffusion rate. So the arrival rate on the first one, and from the second one is surface diffusion, chemical reaction, nucleation, growth, bulk diffusion. And then we say on the surface, there is a energy. Okay, this is energy. So if R greater than 1, this process reduced, right? We talk about that. So sputtering metals, can we use DC or RF? In fact, we can use both. Sputtering alloy and compounds, we just need to concern about the sputtering yield. Okay. The sputtering target, we need to be careful about the temperature. Okay, the temperature, target temperature. Basically, there's no diffusion, and we want to make sure the surface enriched in low S component. But for the evaporation temperature, you see that you will generate a very high diffusion, and you found that all the composition change and the species change in the entire source. So any question about my talk? This is a talk. This slide is a talk of sputter deposition, and later on I will give a talk at the evaporator. Okay, I will give a talk at the evaporator. But before I go to the evaporator, so any question in the sputter? Okay, so if no further question in the sputter, we will let's take a 10 minutes break. We'll come back at 8:35, and after that, I'm going to talk about the